This is going to be the third and last lecture by Shraddha. And after this, after the tutorial, I will also share a form with all of you, to give feedback about Shraddha's lectures. Thanks. Shraddha, you may begin.
Okay, thank you. So, good morning to everyone. Today, there are two main things. Of course, to look at to complete the proof of Wiles theorem that we have done in very one specific setup, and another one is to understand finite dimensional representation of SL2C. And I want to say this SL2 is so important that, of course, you will encounter when this workshop continue. And just to say, I mean, one can even have just one entire book on SL2C modules. And so this is very nice book. Have a very full treatment about SL2C modules. You can have a look on it, which not only concerned about finite dimensional, not only necessary weight modules. So if you are interested, you can have a look on this, and I will be also following somewhat closely this book, and which does not affect too much. I mean, it's still you can do the way things are done in Humphreys or any other book. Everything is same. So before I start completing proof for the Wiles theorem, I want to ask why SL2C. Okay, yesterday's tutorial, we have seen SL2C is simple, and we have in lecture we have also seen that every semi-simple Lie algebra is direct sum of simple Lie algebras. So perhaps one should start understanding first representation of so-called simple algebras, and so which simple Lie algebra is actually smallest in the sense of dimension. So the question is, does there exist a simple Lie algebra of dimension 1? So would someone like to, who has not seen Lie algebra before? Of course, if you have seen, you know the answer. But if you have not seen, you can try to think and say some words about it. So the question is, do you have a one-dimensional? Of course, there are one-dimensional Lie algebras. You can start any vector space, and then what can you say about the commutator? If it's a one-dimensional, then what has to be the commutator? Can it be general? Can it be anything? Or it has to be something very specific? It has to be something, right? So V is, let's for the time being, let us just write F for field, any field, the span of some, I mean, it's just something like some vector V. So on this, if there is, what are the possible commutator on this vector space, which is just one dimensional? So, okay, start playing with it. So everything is scalar multiple of one single vector. So alpha V, beta V, right? This is one dimensional. So every vector will be the scalar multiple of this single. And now, if it's a commutator, the commutator must be bilinear. So you can take out alpha, beta both outside, and you get commutator of V with V. So if and then from the axiom 1, it has to be 0. So on one-dimensional Lie algebra, the only way you can do is have the commutator to be 0. So okay. So now okay. So now you understand how does a one-dimensional Lie algebra look like? Will it be simple? If you know the definition of simple Lie algebras, we have defined in both previous lectures. It does not have any non-zero proper ideal, and as well as the commutator, the derived algebra should not be 0. But here the only way the commutator you can define on this one-dimensional one, it has to be identically 0. So no, there is no one-dimensional simple Lie algebra of dimension 1. Okay. So of course, so okay, so after dimension 1, we can move on dimension 2. What about dimension 2? Is there a simple Lie algebra of dimension 2? How will you start? You can start playing, right? Just like here, start some vector space, take two vectors and see what are the possible things.
F square.
F square. Okay, so I guess what Anna is saying is that let's just take f direct sum f or just something which is generated by 2. Okay, so this is just a vector space, that what he said. A two-dimensional vector space over a field, you can pretty much like up to isomorphism can write this. And so what about the commutator? What are the possible commutators? So it has basis, right? So you can write some, let's say, basis x and y, right? This is for this one, right? So now, so what are the possibilities for the commutator? So of course, the one thing is that since commutator is bilinear, it is enough to define the commutator for all possible commutator for basis element, right? So possibility one is that you declare it to 0. So the moment you declare it to 0, if then the entire commutator on the entire this two-dimensional vector space has to be identically 0, because there are this is just two-dimensional. The only possible non-zero commutators could be xy, commutator of xy and yx. Then commutator of xy is same as is minus of commutator of xy, yx. So if this is 0, then every commutator has to be 0. So in that case, your V will again become abelian. All right. So what about in the so the question is, can you define a non-zero commutator? So can it happen? So answer to this is, it is possible. So you can write so okay, suppose this is there. Suppose you can have a commutator where the commutator of this basis, the only important commutator is commutator of x and y, that is non-zero. Then in that case, the derived algebra, okay, probably I'm you might be bit not comfortable me writing V, so let me write L, because L was the notation that but I am starting with the vector space and analyzing the possible commutators. So in that case, the derived algebra L comma L, what can you say about this? Since it is not 0, it is definitely not 0, but can it be entire? It is not possible, right? Because just from the definition of the commutator derived algebra, it is a span of all possible commutators, and the only commutator rest every commutator is going to be actually scalar multiple of the commutator of x with y, because of bilinearity, and L is just two-dimensional. So this, if it's non-zero, then this is going to be dimension 1. The derived algebra is going to be dimension 1. So I have not constructed a two-dimensional simple Lie algebra for you. But from here, sorry, I have not constructed a two-dimensional Lie algebra for you. But from here you can now immediately say that it is not possible to have a two-dimensional simple Lie algebra, right? Because in the first case, it will be identically 0. L will become abelian, not possible. Again, the commutator is 0. We in simple Lie algebra, we put the condition that the derived algebra must be non-zero. And in the second case, it is non-zero, all right, but it's but in that case, what happens is that the derived algebra of L with itself becomes a non-zero proper ideal of L. This is ideal, right? And this become non-zero proper ideal. So no matter what you do, you can never have uh, mm, a simple Lie algebra of dimension 2. It is possible to have Lie algebra of dimension 2 where commutator is not necessarily this, and there is only one possibility. I leave up to you to play around with. It is possible to have, but the answer here is that there is no simple Lie algebra of dimension 2. Okay, so we move on to 3. So do you know any simple Lie algebra of dimension 3?
SL2C.
SL2C, very good. So here we know SL2C. Sorry, I should be consistent with the notation, that at least I should not interchange between my own notation, SL2C. So this Ritesh did elaborately in yesterday's tutorial, that SL2C is a simple Lie algebra and dimension of SL2C is 3. So at least we have one example to begin with. Okay. So I will come and so this is the first, this is the the most I mean fundamental example to start for a simple Lie algebra, where we can ask its representation theory. So not only is the first one is actually the important one. You will see that knowing a lot about SL2C representation, or in general SL2C will keep coming. Even if you are doing higher dimensional arbitrary semi-simple Lie algebra, SL2C will keep coming. So it is very important to have its uh, full picture independently. Okay, so now I'll go to, so this is kind of the motivation for today's lecture, that why, I mean, we are going to look at representation of SL2C right after we complete theorem, proof of Weil's theorem. So let us now go back to Weil's theorem and try to complete it.
Ma'am, is it like SL2C is the only simple Lie algebra of dimension 3 or something?
Yeah, it's going to be the case.
Okay.
Okay, so I'm recall in Weil's theorem say every semi-simple Lie algebra. If I mean, if you look at a finite dimension representation of semi-simple Lie algebra with the proper condition on your characteristic field, then you can write V as a direct sum of irreducible representations. And then we said that it is equivalent to proving that if we start with any representation, any sub-representation of V, I can find its complement W prime, which will also be sub-representation. Complement means I can write V as a direct sum. And then W and W prime being the smaller dimension, you can keep on breaking until you make you arrive at full decomposition into irreducibles. So this is the main claim. And we did prove this main claim in a specific case. Moreover, before that, we also said you can actually assume that your phi is faithful, where phi is a map defining the action of L on V. And so last lecture, what we did is that, so we have to find a complement, right? So let us start where complement is small. So of course, since it is proper, then the smallest thing is one dimension. The complement should be one dimensional. That means we should have a dimension of the W sub-representation that we are starting with. That should be only one less than the dimension of V. Okay. So, so we did this is in this case, if W dimension of W is only less than one less than dimension of V, then W is irreducible, and sorry, and W is irreducible. Under this specific setup, we were able to show that we were able to find a complement for the W. And the complement was what? Complement was precisely the kernel of, sorry, this is wrong. I should written kernel. The kernel of L linear map, which is very specific map, is or it's also called the Casimir element. So, and moreover, I mean, because kernel of L linear map is also a sub-representation. And we had observed some important thing about this Casimir element was that so if W is irreducible, and then this Casimir element, when you restrict to W due to Schur's lemma, it is going to act by scalar, and further we were able to say that it is acting by a non-zero scalar, and that was kind of allowed us to write V as a direct sum. So a lot of hard task and main idea was done so far, and now it's just like a lot of linear algebra and some module that we are going to construct, and but all of these are actually motivated from what we have done in this specific case. So okay, so let us complete the proof. Again, some various steps are done. So again, the first step is that
The
to
partial with
complete.
respect to y.
Sorry.
Ma'am, this Tanisa, she is asking that is SL2C the unique simple Lie algebra of dimension 3 or it is unique up to isomorphism?
Up to isomorphism, of course.
Yeah.
So
There was another question. Yeah.
yeah.
Can you
What is
please
that?
repeat?
What is the question?
Yeah, there is this from Bappa, right? Unique
No,
up to
there was some
isomorphism.
other person talking. Can you please repeat your question?
Is SL2C the unique simple Lie algebra of dimension 3 or it is unique up to isomorphism?
That was already we said, right? To isomorphism.
Yeah.
Anyway, so I'm moving on. Okay, so the point is that we want to yeah, so you want to first complete the proof when the dimension is when the dimension of this sub-representation is only one less than the dimension of V. And actually one terminology will keep coming. I may just simply say it. So please note that this is a co-dimension. Saying the dimension of W is less, it's only one less than the dimension of V. It is equivalent to saying that the co-dimension of W is 1. It's basically saying that co-dimension of a vector subspace is the dimension of V minus the dimension of W. So saying that the dimension of W is dimension of V minus 1 is equivalent to saying that co-dimension of W is 1. So I may just keep saying this co-dimension thing. Okay, so having proof in this specific case, so let us move on. So for any so where I will just write the proof where we want to compute. So for any W sub-representation of V with co-dimension of W equals to 1, there exists W prime such that we can write W as W direct sum W prime. Sorry, we can write V as a W direct sum W prime. This is what we want to prove. So we are going to prove by induction on we are going to prove induction on dimension of W. Okay. So our base case is if dimension of W is 0. If dimension of W is 0, then in that case what happens? Then the dimension of V is 1. And by definition of a simple representation, every one dimensional is irreducible. So in that case, nothing to do, right? And so then so we are basically going to prove in induction. So let us so I will also like to write the induction hypothesis in this case. So for every induction hypothesis is that so for every representation U of L says that dimension of U is strictly less than dimension of V, every co-dimension 1 sub-representation of U, every co-dimension 1 sub-representation of U has a complement in U. Okay, so this is induction hypothesis. So now let us go to induction step. So I will say the like some important things, and but where only linear algebra is done, like some check that intersection is 0 and everything, that I am going to leave, because this you should place, then you also get the idea what is happening. Now since okay, so okay, so we have already done this. So there were two cases in the induction step. that this co-dimension one sub-representation that we are starting with, it can be be irreducible itself, or it need not be irreducible. So if it was irreducible, we have done in this case. And if it's so today we are going to do when it's not necessarily irreducible. So in that case, we will have non-zero proper sub-representation of W. So let W prime be a non-zero proper sub-representation of W. Okay, so somehow now to use the induction hypothesis, somehow we want to put this W prime in some another sub-representation of V, such that where this W prime will become co-dimension 1, and then we can use our induction hypothesis to do something. So the way to locate that W tilde is basically, I'm saying, so we have this big representation V. Inside this, we have started something. We have W and also W prime. So we want to put this W prime inside some W tilde, such that W prime becomes co-dimension 1 in W tilde. So the idea is to look at the quotient. So look at this V mod W prime. So V mod W prime, the dimension of V mod W prime is definitely strictly less than dimension of V, right? And the point is that if you look at this W mod W prime, which is a subspace of, not just subspace, in fact, a sub-representation of V mod W prime, in that case, the W mod W prime has co-dimension 1. So W mod W prime co-dimension 1 in this, wherever it is sitting, you know where it is sitting. So now we can use induction hypothesis to find a complement of W mod W prime inside V mod W prime. So by how does subspace correspond in quotient space. So by induction hypothesis, there exists W tilde containing W prime, such that V mod W prime is equal to W mod W prime direct sum W tilde W prime. Okay, this we can do. This is coming from the induction hypothesis, and this is where some claim that I am not going to do, because this is dimension counting. You have to basically, the dimension of the quotient, and you can get some information about the dimension of some relation between dimension of W tilde and W prime. So you can check it. So dimension of W prime is actually dimension of W tilde minus 1. Good. So now we have located a sub-representation of V where W prime is actually co-dimension 1. So again, we can use induction hypothesis, right? And why? Because first of all, before using induction hypothesis, note that dimension of W tilde is also strictly less than dimension V. And W prime is a sub-representation of W tilde, which is of co-dimension 1. So again, I can use induction hypothesis. So there exists some sub-representation of W tilde such that W tilde is W prime direct sum X. This is again due to induction hypothesis. And now I'm saying in this case we are done. So the claim is that here now V is actually W direct sum X. So how we are going to check? So it is very easy to check that dimension of V is actually dimension of W plus X plus dimension of X. So first of all, dimension X is what? I mean, dimension of X is 1. Everywhere the complement is complement of a co-dimension 1 is dimension 1. So this is 1. This is dimension 1. And we have already started with dimension of W, W co-dimension 1. So this is very easy. And the second thing is also you check that this W intersection X is 0. So if you combine these two, you can have your claim. And we are done in the case when the codimension of subrepresentation is 1. Okay. So let us move on to the general case. I mean, where we are not going to assume subrepresentation whose complement we want to find is codimension 1. So before that, I will just write that. So the main claim that we wanted to prove is obtained for any codimension 1 subrepresentation of V. So this, for the codimension, we are done in full generality. So now let us move on where we not necessarily have codimension 1. So in this case, now let W be a subrepresentation of V, not necessarily codimension 1. That case we have done in full generality. So if you go back and see how we were doing codimension 1, in particular W was irreducible, we were kind of somewhere this Casimir element appeared and we started looking maps, and that was very important. So somehow we will try to do something similar. So now look at this vector space, which is all the F linear, means all the linear maps from your V to W. So last lecture I have included how does if V and W are representation of L, then how does the Hom space also become the representation. I have added that, but I did not say that in the lecture. So I'm just going to say how does M is also a representation of L. So to say that M is also representation of L, you start with any X in L and take a linear map from V to W. If you have not seen how you do this in case of groups, so this will look very new to you, even if I say some motivation and idea. Otherwise, you just take this as a definition. So we want to define X dot V. So X dot V should also be mapped from V to W, linear map. So we should evaluate at some V. So it is defined as applying X to F of V, which is element of W, and minus with F of X dot V. And if you have seen how you make this kind of thing in representation of groups, how you make the Hom space representation of a group when both the V and W are given representation of a group, then I can say that, so when whatever you do in case of group, when the similar thing happens in Lie algebra, where you think that some kind of derivations some kind of differentiation or derivation is going on. So if you know your formula for in the case of group, then this one is you can think of some derivation, and then in that case you can remember. And I'll leave it to you check. It actually indeed define the action of Lie algebra L on M. So okay, so this is also a representation of L. And inside that we are going to look at certain subrepresentation. So let me go to call it M. So we are going to look at all those linear maps such that when I restrict it to W, I should act as scalar on W for some scalar in your field. And why I started to do, you see, I mean, again, I'm thinking what happened in the irreducible case when W was irreducible codimensional. The Casimir element was satisfying this kind of thing. And inside this, I am going to look at all those ones on which actually F is acting. When you restrict your F linear map, it is actually acting as 0. So you can, it is very easy to check is, of course, M0 is a subspace of M1 on the nose, that the way things are defined. And of course, okay, one more thing you have to check that both M1 and M0 are actually subrepresentation of M. They have also action of L. And M0 is a subrepresentation of M1. Moreover, the The co-dimension of M0 in M1 is actually 1. So dimension of M1 minus M0 is 1. You can check that. Okay, so now we are in a setup. So we have M0, a sub-representation of semi-simple Lie algebra, we have a sub-representation M0 of M1, where M1 is a representation of a semi-simple Lie algebra, and the co-dimension of M0 is 1. So I can use the previous case where we have done about the co-dimension case to obtain a complement. So from co-dimension case 1, from the co-dimension 1 case, there exists a C sub-representation inside M1 such that M1 is M0 direct sum C. And where dimension of C, so this is a complement for the co-dimension. When 1 means the dimension of C is 1. So my C is going to look like something span of some one linear map psi, where psi is a map from V to W, and psi restricted to W will be some lambda times identity on W, and this lambda is not 0. Why? Because it is complement of M0. If it was 0, then it will land in M0. It cannot be 0. Then after then we are very close to just say the idea what we did for the irreducible case when we had the Casimir element. So if somehow I can say that my psi is L linear, then a complement for W would kernel of this psi will serve as a complement of W, will be done. So why so this is something that we did in tutorial last time. So L is semi-simple, that is given to us, and C is a one-dimensional representation of L. So this L must act trivially on C. This we have seen last time. The only one-dimensional representation of a semi-simple Lie algebra is the trivial one. It cannot be anything else. So what does it say? So it says that x dot psi must be 0 for all x in L. And now if you expand the meaning of x dot psi, how does it act? It precisely says that x is L linear. Sorry, psi is L linear. Okay, then after that we are done. So we have a L linear map. So we have a L linear map psi from V to W. This is L linear. So, and the restriction of psi to W is lambda times identity on W, and lambda is not 0. So given this much, you can easily prove that V is actually direct sum of W and kernel of psi. Since this map psi is L linear, the kernel of psi will be also a sub-representation of V. For arbitrary linear map, this may not be the case, but since psi is L linear, this is true. So we have completed the proof for Weis theorem in full generality. Okay, so any question before we move on to representation theory of SL2C? Okay, if not, let's move on. So Weis theorem says, so we want to understand finite dimensional representation of Lie algebra SL2C, right? Okay, so due to Weis theorem, it is enough to understand irreducible representation, right? Because Weis theorem says that every finite dimensional representation you can write as a direct sum of irreducibles, and SL2C is semi-simple. In fact, it is simple. So what we are going to do to understand finite dimensional, it is enough to understand so-called the irreducibles one. So here are some facts about more than facts. This is recalling. We have been seeing this somewhere, at least in tutorial. It came. I mean, previous lectures or tutorials. SL2C has come. So SL2C is all your 2x2 matrices over the field of complex numbers, such that the I don't know what I said about SL2C. I'm just going to repeat it. So SL2C consists of all 2 cross 2 matrices over C such that trace is 0. And the commutator is this AB minus BA. And we have a basis for nice basis for the Lie algebra SL2C. It is we are going to fix some notation also. So E is this 2 by 2 matrix, and H is this matrix, and F is this matrix. And we have also computed these commutators, which are the only relevant commutators, because rest of them either negative of these or 0. So yeah, so this is all about SL2C as a Lie algebra. Okay, so now let us move on to the representation theory part. So one more thing before we move on, what I mean, looking at these matrices E and F and H, can you say anything about that from the linear algebra, like something that you something you see, something you want to see from the matrices? This is specific matrices, right? Do you want to say something about how? I mean, what can you say about E and F as a matrix? Forget about Lie algebra for the time being. As a matrices and linear algebra, what any result from linear algebra that you can say, oh, E is this, F is this, and H is this.
Trace zero matrices.
Trace zero matrices, that is definitely true. But any other thing, that is true. All of them are trace zero. Okay, but can you say something where E and F belong, but H is not? H is in some another class.
Nilpotent matrices.
Yeah, exactly. So E and F are nilpotent, while H is your diagonal matrix, right? So, I mean, in particular, there are differences between the non-zero. I mean, these are non-zero nilpotent matrices, in fact. Okay, so I'm going to move on to representation theory part. So let us start with a non-zero finite dimensional irreducible, of course, irreducible representation are non-zero, so I don't have to say this. Let V be a finite dimensional irreducible representation of SL2C, and let us start analyzing this and what kind of information we can have about it. So the first thing that I'm going to do is going to look at the so H is acting on V, right? Everything is acting. E is acting. So V is a representation of SL2C. So I can think of E, because E is acting on V, I can think of as E as a map from V to V, and likewise H is a map from V to V, and E and F is also a map from V to V. Okay. Okay, so what we are going to write V as a sum of let us look at when you look at all the eigenvalues of V with respect to H, eigenspace decomposition with respect to H. I'm not saying it exists or it is equal or what happened exactly what will happen, that we are going to reveal. But we are going to focus more on H than E and V. There are some reasons because E and V are nilpotent, but H is, you see, something diagonal. So this is more promising than these two. So let us start with this. So since we are working in algebraically closed field, particularly in fact C. So so we know that when H is acting on V to V, it will have one eigenvalue. So what we are going to do for any complex number, look at this space, which could be zero, pretty much possible. So V lambda all those V in V such that H is acting on V by H dot V, means you are applying this H to V is lambda by lambda times V, where lambda is your fixed scalar in complex number, and this is a subspace of V. It could be zero, quite possible. So consider, I'm going to consider this W, which is going to be direct sum of all V lambda. Lambda belongs to C. This is contained inside V. I'm not saying it is equal. Okay, but can W be 0? Can W be 0? Or can you say if W is why W is non-zero? Or that's equivalent to saying that at least for some lambda, this V lambda is non-zero.
We are taking F to be algebraically closed. I mean, we are taking
Yeah.
complex numbers.
Exactly, precisely. Since C is algebraically closed, so since so answer to this is no. So since C is algebraically closed, so at least one of them is non-zero. So we can. I'm just not going to write which one. Just I'm going to write directly that W is non-zero. Fine. So now we have a non-zero subspace. I'm not saying sub-representation. I'm saying just a subspace of this given irreducible representation of V. Fine. So let us start analyzing action of these E, F, and H on this W. Let us start doing that. Okay. So this is our next lemma. So if lambda is in C, I have written already this. Probably if you have not already seen, let me erase. So if lambda is in C, applying H to V lambda, where does it take? What happens to it? So any answer I already showed you, but we can say. So this one is easy, right? The first one at least. So if you take some vector in V lambda, so if you take some vector in V lambda, so what do you know? So if V belongs to V lambda, then by definition H dot V is lambda times V, right? So if you so we want to understand where does H takes to V, right? No, I
Zero.
want to understand so no, not why 0?
H is nilpotent.
No, H is not nilpotent.
Oh, H was diagonal as well. Okay, sorry.
Yeah. So we have to understand what happens to H dot V. The claim is to see the lemma is asking you to understand H dot V lambda. So we should take any vector in V lambda, apply S to it, and try to analyze. So if you do this, if apply S to this, so this part belongs to H dot V lambda. If you apply S to it, what do you get? So so H dot V in the bracket I can write lambda times V, right? And then action is linear. I can take H outside. I am going to get H dot V, right? This is so what happens? So this H dot so H takes H dot V to lambda times H dot V. So what is the answer now? Can you say now? I don't have to write an equality. H is taking this H dot V to lambda times H dot V. So what should I write here?
Lambda square V.
Why lambda square?
H dot of V is lambda V. So
Okay, so if you are confused, you write this H dot V to be W and then do the calculation. So this H dot V, which is equals to W, is a element in H dot V lambda. So we want to understand what happens when you apply H to W. So when you apply H to W. So what we did exactly, we get this lambda times W. So can you say now H dot V lambda, where does it land? Where does W land? If H dot W is lambda times W, so W is in where?
Belongs to V lambda.
Yeah, it belongs to V lambda again. So the answer here is actually V lambda. So I mean, each of these V lambdas are stable under the action of H. Because these are if non-zero, then these are precisely eigenspaces. If zero, then anyway it is stable, nothing to do. Anyway, so likewise, what about E dot V lambda? So you know how to start. Okay, so let me rather start saying instead of asking much. So you again do this E dot V and apply. So if you call this E dot to be W, okay, I'm just denoting it. W is your E dot V. So if we apply H to E dot V, or rather let me write W, which is same as H dot E dot V, then I am going to use the commutator to simplify it. Commutator of H with E is 2E. That is equivalent to saying that HE minus EH is 2E. So from here your HE is 2E plus EH, right? So I can do that. I can simplify this H dot E to 2E plus EH applied to V. And what is H dot V? H dot V is what? This is H dot V, right? So your V is in V lambda, right? So V is in V lambda. So H dot V is acting by scalar lambda. So 2 times E dot V plus E times lambda V. So you get, if you simplify all, just write it properly, this will become lambda plus 2 E times V. So your H is taking any vector in E dot V lambda to V lambda plus 2. Just keep going. Is there any doubt? Because we did not do anything much. It is just using the commutator and the definition of V lambda. Is there anything that you want me to repeat or ask some question if you have? Okay. Okay, so what about F dot V lambda? What is your guess?
Lambda minus 2.
Yeah, V lambda minus 2. So same proof you do instead of E, now you replace it by F. So that's what I'm going to do here. So write it F everywhere you had. And now, of course, I cannot, sorry, wrong thing I erased. Okay, so now I should use commutator for H and F. So if you use commutator for H and F, then this is what? So commutator of H with F is minus 2F. So this is HF minus FH equals to minus 2F. So you are H dot F is minus 2F plus FH. That is what you are going to write to get your answer. Minus 2F plus FH applied times V. When you simplify it, this is precisely going to be lambda minus 2 F times V. So F dot V lambda lands in V lambda minus 2. So what is the upshot of this? Upshot of all of this is that if I apply any of these E and F and H to W, it will again be in W, because W is what? W is direct sum of all of these V lambda. S takes V lambda to V lambda, E takes V lambda to V lambda plus 2. V lambda plus 2 is also a part of V. And F dot V lambda takes, F takes V lambda to V lambda minus 2, and V lambda minus 2 is also part of W. So W is stable under the action of E, F and H. And then since this E and FH forms a basis for SL2C, so this W is stable is under the entire SL2C for any element of SL2C. Any element of SL2C will be a linear combination of E, H and F. So you can, it will be stable under that. So the upshot is that this W, which is a direct sum of V lambda, lambda is running over complex number, is stable under the action of this, and hence W is actually sub-representation of V. And we have already said that W is non-zero because we worked over the field of complex numbers. So this W must be the entire V. So what do we get? So we get something very nice here, that with respect to action of H, your irreducible representation is, I mean, it's actually diagonalizable. I mean, H is V you can write as a direct sum of eigenspaces for the action of H. Yeah. So action of H on V is precisely this saying is diagonalizable. So any question, any doubt here?
Ma'am, I just had a question where, I mean, do we really need to use C, or can we use just any field since the diagonal entries are 1 and -1 in case of H? I mean, do we really need C to get the eigenvector?
I mean,
Because
characteristic 0 definitely you would need. So
okay.
to say some of, I mean, at least characteristic 2 you must avoid, because 2 is really bad. I mean, lot of thing will be changed. So anyways, let's if that was a question, I will say first let's understand everything over C, and then you can try to ask yourself, okay, if I drop this, then what happens? Of course, some of the things like if you're working with arbitrary algebraically closed field, you can have this. Just see what I mean. What are the things you can have? Like, okay. Okay, so we have to give certain definitions now. So the non-zero elements. This is a terminology. Non-zero elements of V lambda. So if your V lambda is non-zero, then the non-zero elements of V lambda are called weight vectors. And this complex number lambda is called a weight of V. Okay, and all of this I'm just defining when you're provided your V lambda must be non-zero. If it's zero, then there's no definition. Okay, so far we have not used V is actually finite dimensional. This is where now we are going to use. So far whatever we have said, okay, it just works on well we did use somewhere to say that it has a eigenvalue. Otherwise, yeah, so we did use, but we are going to use once more. That time we did not say really explicitly, but we are going to use it in more where it is going to give something more strong. Now since V is finite dimensional, so the summand in this decomposition here, that means this V lambda, infinitely many of them cannot be zero, right? Because then V will become infinite dimensional. So only finitely many summands, that is V lambdas in the decomposition 1 are non-zero, right? Okay, so what does it say? So it says that it says that there exists some mu. So there exists some mu, some complex number C, such that your V mu will be non-zero, and I'm going to write V mu plus 2k should be 0 for all k belongs to natural numbers. Okay. So there exist further, I mean, if this is non-zero, so there exists some non-zero vector, which I'm going to write V sub mu in the vector space V mu, which is such that your V sub mu is non-zero. But when you apply E to that, because E is going to send your V mu to in V mu plus 2, but that is non-zero, but that is 0 because of this. So this must be 0.
Sorry, ma'am. Actually, I forgot to tell you that there was one question in the chat. This V lambda is invariant under H? This love
Yeah.
is asking. Yeah.
Yes, V lambda is invariant in H. That is precisely we did here, right? So these V lambdas are not invariant with respect to action of E and F, but with respect to action of H, they are invariant. These are precisely eigenspaces. I mean, if non-zero, these are precisely eigenspaces for the action of H, and we did it. Okay. So, okay. So V mu is non-zero, but E is going to kill it. Such vector have a name. They are called maximal vector, but we are not going to say much in the detail about this. We don't require much of this terminology. So this is a maximal vector. V mu. Just okay. So when we write this, when we have written this, we kind of looked at only the action of E, because V is finite dimensional. It cannot have infinitely many V lambdas to be non-zero. So now let us start with this V mu and say some more things. So start with this V mu and then start applying the action of, we start applying F to it. So we start with V mu, then apply F to it. So we have you F dot V mu, then you have F square, means apply F twice to V mu, then F cube V mu, continue this. So can this be infinite? I mean, can this set be an infinite set? This is a set of vectors. Can it be infinite? And if not, then why? So reason is that, so your V mu is lies in the space V mu, and this lies in mu minus 2. This lies V mu minus 4. You can continue this. And what do you know from linear algebra? So these are what? These are eigenspace. I mean, if non-zero, then these are eigenspaces for distinct eigenvalues. So the vectors from here will be linearly independent. Sorry?
Ma'am, I mean,
Sorry?
there must be finitely many eigenvalues since F is. So
No, so, sorry, could you please repeat?
I mean, there should be finitely many list of
Yeah, you can say that as well. Yeah. So if these are all non-zero, then I mean, these you're basically saying these itself will become, after a while, these vector spaces will itself become zero, because I mean there can be finitely many eigenvalues only. H is acting on a finite dimensional vector space. So in this list, so all the non-zero vectors. So this is a finite list. First of all, this is a finite list, means so we can actually say that there exist a minimal. We can in fact choose a minimal one, because after that everything is going to be zero. So I mean, if something, it cannot happen if this is this is zero, but this become non-zero. Come on, that cannot happen, right? Because we are applying, this is all powers of f. So this, if something is non-zero, it will be in continuous fashion. It will not be okay, this become zero, but this is non-zero. That cannot happen. So there exists a minimal n such that f to the n v mu is zero, and this is important, then v mu f dot v mu, these are all, of course, all of them have to be non-zero because of minimality. We are assuming it will guaranteed an fn minus 1 v mu. So this is a set of non-zero vectors, and it is not just a set of non-zero vectors, it is linearly independent. This is I need to add age, I guess. Yeah, no, probably no. Is linearly independent. So why this set is linearly independent? Because of minimality, we know none of them are non-zero, but why it is linearly independent?
They correspond to distinct eigenvalues.
Yes, exactly. So each of these vectors correspond to distinct eigenvalues. So they must be, we know this result from linear algebra. So they will, this is going to be linearly independent. So let us, every time instead of writing f to the power this, let us fix some notation. So I'm going to write v0 as v mu and vi to fi dot v mu, and I is from 1 to n minus 1. And let us call this u to be span of, rather let me add the page, span of v0, v1, vn minus 1. Okay. So so your v is actually decomposing in very nice way. So, and this is actually your u is nothing but actually the irreducible representation that you begin with, right? Because we have actually, so perhaps maybe so what can you say, maybe perhaps before this? So okay, fine. Okay, let me not say. I think I need to, okay, I need to, if, okay, so this set, this u is written, the way it is written, it is closed under the, I mean, if I apply f to any of the element, it will again be in u. If I apply any element of h, it will again be in h. So somehow if I can guarantee, if I apply e to any element of this, any element in this, then it will again be here. Then somehow we can use irreducibility of v to show that this is actually equal. This further simplifies your irreducible representation. And I think that is what was my next thing. So from the construction of u, u is stable under the action of f and h. So let us find how does E act on those vectors. E dot vi, what is that? So answer is already written here, but let us see why it is the case. So first of all, already you know that E dot v0 is 0, so nothing to do. So now let us see what happens it does to a basis vector. Yeah. Hello. Hello. The question. So anyway, we are going to apply induction on I. So if I equals to 1, then let us compute E dot v1. So what is E dot v1? So v1 by definition is f dot v0. All right. Now you can use your commutator. So commutator of E with f is h, right? In the beginning we have said. So apply the commutator. So this is f dot 0 plus h times v dot 0. Very good. So now we know that E acts on v0. E acts on v0 by 0. So this part becomes 0. And we are left with h dot v0. And v0 is an eigenvector for h corresponding to eigenvalue mu. So we have mu v0. So this is precisely, you can just write it as a 1 times mu times minus 1 plus 1, 1 minus 1, which is basically v0. I don't want to write 1 minus 1. Okay, so now we can do it inductively. So suppose you know how to do this for I minus 1. Let us prove it for I. So E dot Vi. So idea is to, this Vi is defined in terms of Vi minus 1. Vi is precisely f applied to Vi minus 1. Then again you do the commutator business. So you get Vi minus 1 plus h Vi minus 1. Okay. And from the induction hypothesis, you can write E times Vi minus 1 expression. So let us write that. So it will become I times, what will become? I minus 1 times mu minus minus I plus 1, then plus 1 again, 2 V I minus 2. Fine. What about this? Now, how can we simplify this one? So recall each of this V1, V2, let me erase this page, which is will cause unnecessary. Yeah. So each of these V0, V1, V2, Vn minus 1, these are eigenvectors for H, right? And the corresponding eigenvalue also we know, because this is eigenvalue mu. This will be mu minus 2. This will be mu minus 4. And this will be mu minus 2 times n minus 1. So what is this? Can you tell me now? H acting on Vi minus 1. This is going to be mu minus 2 times I minus 1 Vi minus 1. Now you simplify everything. F times Vi minus 2 is by definition Vi minus 1. And if you simplify this, this is precisely becomes I times mu minus I plus 1 Vi minus 1. So recall this, I'm probably right for you, that F Vi minus 2 by definition is Vi minus 1. Okay. So what do we observe? So these on these vectors, actually E is also acting very nice. H is acting by scalars, these vectors, and F is just moving one, V0 to V1 and V1 to V2 like that. But your F is also, your E is also acting nicely. First of all, E is killing V0 by, that is the how we have located our V0, and it is sending V1 to some scalar multiple of V0 and V2 to some scalar multiple of V1 and Vn minus 1 to some scalar multiple to the preceding vector. So from this it is clear that now we can say that this U is actually also stable under the action of E. So U is also stable under the action of E. Okay. And we have already said that U is stable under the action of F and H. So U is actually stable under the action of any element of SL2C. So and U is a so U becomes so U is a sub representation of my irreducible that you begin with V. But since V was irreducible, this will imply that U must be V. Right? So, okay. So as V is irreducible, this implies U must be V. So in fact, my V is nothing but a span of these vectors V0, V1, V2, Vn minus 1. Okay, so now the question, so and perhaps one should write that here you have H dot V0 is these are important data. H time V0 is this, and E acting on V0 is 0, and Vi is F apply I minus times to V0. Okay, fine. So can this so this mu was some arbitrary scalar in the complex numbers? Can it be really arbitrary? This is something that we want to understand about mu. So this is actually just kind of an idea that one gets from here. So doing this computing E dot V0. So if we compute sorry, not E dot V0. So we compute E dot Vn in two ways, then whatever we compute, they have to be equal, and it's going to give some condition. So E dot Vn, from whatever we have done previously, from there we can say E dot Vn is n times mu minus n plus 1 Vn minus 1. All right. Now you should say that by definition this Vn is actually 0. F is the way we are choosing, we have chosen n. F dot F dot Vn minus 1 is by definition F dot Vn minus 1 is Vn, and it is 0 because n was the minimal. N was the minimal says that F to the n times V0 was 0, and n is minimum satisfying this, right? Fine. So so this no matter what, I mean 0, I mean, so E dot Vn from this, your E dot Vn also should be 0. And from the previously what we have discussed, we have this. So you equate all of this, you get n times mu minus n minus 1, Vn minus 1 should be 0. Now this can only happen provided this part is 0. This, because Vn minus 1 is a non-zero vector, n is minimum, right? So this says that n times mu minus n plus 1 should be 0. But then n is non-zero, n is non-zero. So this says that mu should be n minus 1. So this is, so the weight is that the weight mu is not arbitrary. It has to be n minus 1. And also since we have said that this V0, V1, V2, Vn minus 1 are linearly independent, and V is a span of this. So that this is the dimension of V is n. So what from where you have to start is, this is actually mu is
Shraddha,
nothing but
sorry to
dimension of V.
interrupt, but we should at least give 10 minutes break to the participants here.
10 minutes break for what? Is it 11?
Oh, sorry. I thought it was 10:30. I'm sorry.
Okay, you scared me.
I
was like,
was
did
scared
I?
as well. Sorry.
Fine. Okay. So we have 15 minutes, more than 15 minutes, something.
Hey, you can also take extra time if you wish. Yeah, but yeah.
No, I'm not going to take. Sorry. No, hopefully I will be able to do it. Okay. So let us again summarize all of this, what is happening. And there is a nice picture about this representation that the way we have started, suppose there was some irreducible representation, then we kind of, analyze how it's going to look like. Soon we can say actually one can even construct a irreducible representation in the same fashion. But before that, let us write it in more, kind of collect everything. So what we have, that V is a span of these vectors, okay? And each of them are eigenvector corresponding to different eigenvalue of for the action of H. And so V0 is precisely was eigenvector corresponding to eigenvalue mu, but we have just computed mu has to be n minus 1. And so V1 is going to be n minus 1 minus 2, which will be Vn minus 3. And you can write it all the way to here. So all of this that we have discussed, we can put it in a nice picture as follows. So we have vector V0, we have vector V1, we have vector V2. Continue all the way. Vn minus 2, Vn minus 1. Right? So what is F doing? For F, I am going to use this purple. So F is sending V0 to V1 with no scalar everywhere. So when I'm putting something above the arrow means up to scalar or something. So whatever is the scalar is going to appear. So here is actually just scalar 1. And F is send V1 to V2 and like this. And F sends Vn minus 1 to 0. So I'm not going to write what vector to the arrow, but I'm going to emphasize on scalar is acting. Okay. So this purple is for action of F. All right. So what about, let us do the action of H. So all of this V0, V1, V2, Vn minus 1, these are eigenvector for the action of H. So here V0 is the eigenvector corresponding to, so eigenvector, H is sending V0 to itself up to some scalar multiplier. So the precisely scalar multiple is n minus 1, and Vn is sent to Vn minus, again a scalar multiple of Vn, V1, which is up to scalar, it is this is again Vn, but and the scalar is n minus 3. So here is, you have n minus 5. You can continue. Minus n minus 1. Okay, now let us go to the action of E. So E is killing V0. So I'm going to write 0 here. And E sends V1 to V0, some scalar. So I'm going to write the scalar A1. and then again sending v2 to v1 up to some scalar v2, and here I am, so the red is for the action of E, and here the scalar is I minus n minus I. You can just check is exactly what we have computed, and your blue is for action of H. So very nicely you can depict representation irreducible, if you had a irreducible representation of SL2C of dimension n, then you can write in this kind of picture. There will be these vectors satisfying this, and so this is in terms of picture, this is precisely your irreducible representation. Now the point is, okay, this is all we started with irreducible representation, but what is the guarantee that there is a reducible representation of this thing, of this type? So one way is kind of abstract. You can say, okay, I will start formally with these vectors, v0, v1, v2, vn, and I'll make the action of E to be like this and action of S to be like this according to the picture. And then I will show that this actually becomes a module for SL2C. That's the one way to do it. And it's a calculation that I'm not going to do. You can do it. And another way that there is a problem in the tutorial, you can realize irreducible representation inside some polynomial ring. So let us do that in tutorial, not now. But the upshot of all of this is that given any natural number n, there is irreducible representation for SL2C. Okay. So first of all, you start with, formally you can start with the vectors v0, v2, vn minus 1, and let your E, F, and H act according to the picture. You define a formal vector space. I mean the Vn, which is just take the formal linear combination of the vectors, and the action is according to the picture. You check that it is actually SL2C module. Okay. So what is the guarantee that it's irreducible? So let us address that. So if I define formally a representation like this, so then we have to also address why it is irreducible. So this is all basically going to give us a classification of irreducible representation of SL2C. Okay, so we start with a natural number and this representation then of SL2C. Then the claim is actually simple. So the point is that if we can show that every non-zero sub-representation of V to the n is the entire Vn, then we'll be done. So the point is, so start with. So let M be a non-zero sub-representation of Vn. Okay. Then the claim is that M is actually entire Vn. So since M is non-zero, there is a non-zero vector, right? And you can express this vector v in terms of linear combination of these vectors, right? So when you apply e to the n to v, it is going to be 0. Because you apply e to the n to any of these vectors, it is going to be 0. And v is your scalar linear combination of these vectors. So what it is saying that if you look at the kernel for the action of E from Vn to Vn, and you intersect with M, this is actually non-zero. Because it can happen that E is killing V before this power. That is fine. All I am saying that there is a vector, there is a power of I, there is a power of E which is going to kill E. And it is guaranteed because E to the n is definitely killing it. And V is a non-zero vector. So there is some non-zero vector in the intersection. Now the point is that if you go and look at your definition for V to the n, so dimension of, so not just the dimension, your kernel for the action of E on this representation Vn is actually precisely span of the vector V0. It's actually one dimensional. It's one dimensional and it's actually spanned by V0. So, Okay, so what happens then? Then it says that if you combine all of these two, it says that V0 must be in M. The moment you have V0 in M, you are going to apply F2, because M you started with the sub representation. You apply F to it, all the required powers, you are going to get each of V0, V1, V2, Vn minus 1, they are in M. So this M is going to be entire Vn. So this says that formally that we have constructed a representation is actually irreducible representation, and if you want a more concrete construction of irreducible representation, it can be done inside a polynomial ring that we'll do in tutorial. And further, actually, this Vn and Vm minus 1, they are isomorphic if and only if n equals to m. So if your natural numbers n and m are different, then these representations are also different. All right. And then how we started analyzing representations of SL2C, irreducible representation of SL2C or simple module for SL2C, both mean the same. You can see that there will be an n, not n. In fact, that n is precisely the dimension of V, so that V is going to isomorphic to the formally defined representation. So this gives a complete classification for simple modules or reducible modules, finite dimensional for SL2C. I should say this SL2C. Okay, so this was the classification part. One can have another some interesting observation for this from what we have been doing about simple representation of SL2C. But before that, do you have any question? We still have 8 minutes, and I more thing that I want to say, but before that, do you have any question? Okay, seems no. Okay, so okay, so we have understood we know how does irreducible representation of SL2C look like. So now if you start with any finite dimensional representation of SL2C, you can use Weis' theorem to write down V as a direct sum of irreducibles. In fact, the corollary is saying that it is going to give some condition on the when you write the representation, any finite dimensional representation into direct sum of irreducibles, precisely those V to the n, it is going to give the condition on the number of V to the n that appears. So it says that in any decomposition of finite dimensional representation of SL2C, the number of summands in the decomposition is precisely the dimension W0 plus dimension W1. So I must say what is the W1 and W0. So here W0 is eigenspace corresponding to the eigenvalue 0, and for the action of H. And likewise, W1 corresponds to the eigenspace corresponding to eigenvalue 1 corresponding to eigenvalue 1 again. So why is that? So this is easy. All you have to do is that look at your irreducible representation V to the n. This is whatever we have discussed. It has this kind of decomposition. Don't confuse, this is a decomposition into irreducible. This is a decomposition with respect to action of H only. So this is eigenspace decomposition for the action of H, right? So now you just play with what happens. So when n is even, when n is odd, it is going to give you something. So V0, so both V0 and V1 do not appear at the same time in V to the n. Because see, depending on your n, if your n is odd, then n minus 1 will be even, n minus 3 will also be even. All of this term, these things are going to be even. And if your n is even, then this all of these are going to be odd. So they are both not going to appear at the same time. And so when you write one more thing to say, that when you write your v as a direct sum of v to the n, which can possibly come with certain multiplicity. Let's not worry about that. Sorry, w. So your w0 is precisely direct sum of vn m0. That okay, I should be zeroth eigen. Okay, I should have somewhere some. Okay, let me write this dependency on n as well. So this is the zeroth eigenspace for the which I'm just writing v0 in this setup, and similarly for the odd one. Similarly for odd one, I'll just write similarly. So this observation is actually very this corollary is very useful when you try to decompose a representation of SL2C into irreducible. So one of the thing that occurs a lot in representation theory, particularly in Lie algebra and representation theory of Lie algebras and groups, or whenever you can talk about tensor product. So just quickly, I will just define the action on tensor product. I am not going to say much about that. We'll have some question in tutorial. So tensor product. So if V and W are two representations of Lie algebra L. So the tensor product V tensor W, you take the tensor product as you take for the vector spaces. Then this also becomes a representation of Lie algebra L. So you might have seen this kind of thing in the groups. We can do similar thing in Lie algebra, but with some appropriate changes. So if your X is in L, and it is enough to define the tensor product on this kind of tensor, because then you can linearly extend X dot V. So you can, so the action is defined to be X dot V. I mean tensor W plus V tensor X dot W. It's not like it's not a diagonal action as we do in the groups. Here it is like a product rule for the differentiation. Okay, so the interesting thing that we are going to that one is very interested to what is how does this decomposes V and tensor Vm. If I take two irreducible representation of SL2C and take their tensor product, and from Weil's theorem we know that we should be able to write into direct sum of irreducibles of SL2C. The question is how. So that we will do by examples, some specific values for n and m in tutorial. So I'm going to stop. Thank you. Let me know if you have any question.
Ma'am, what do you mean by writing that W naught is a direct sum of V naught n to the power m?
Now, where is it? Here?
Yes,
Here?
ma'am, top right. Yes.
Okay, so let's do that. What do I mean by that? So from Weil's theorem, I can write W as a direct sum of various irreducible representation with possibly some multiplicity, right?
Yes, ma'am.
This I can do. So now, so the eigenspace, if you look at the eigenspace, zeroth eigenspace for the action of H, that is precisely, that means W0 by definition, is going to be the direct sum of zeroth eigenspace for the action of H for each of these, which I was using just W0. So V and W0 consist of all those V in V such that H dot V is 0. Right? This is again you can think of linear algebra, right?
Okay, ma'am. Yeah, okay. Understood.
Ma'am, I had a question.
Yes.
In one of the previous slides, you had mentioned that the number of summands will be the direct sum of dimension of W0 and dimension of W1. We're looking at the number of summands. So what do we mean by direct sum of
Precisely. Thank you. Thank you. Yeah, that's a typo. I was doing a lot of things. This is sum. So what she is saying that what do you mean direct sum of numbers? No, this is sum. Thank you. Thank you. That was a typo.
Ma'am,
Yeah.
actually here 0 and 1 eigenspace we took means integers are the possible eigenvalues, H eigenvalues. Is it?
Say it again. I did not understand.
No, we decompose V as a direct sum of irreducibles,
Right.
and then number of irreducible component is just number of times 0 as a eigenvalue, H eigenvalue plus a number of times 1 as eigenvalue. Means
Yes.
integers are the possible eigenvalues here.
Yeah, precisely. Integers are the
Yes.
possibles. Yes.
Yes.
Yes. That is one more observation actually that one should say. Yes. Thank you.
Thank you.
Or all the weights of SL2 so given by set of natural numbers. So, Bappa, your question is related to the participant. Sorry, I not saying your full name, so it's not easy for me to say it. It's the same thing. Instead of natural numbers, it's actually integers. And they come with, like, if mu is appearing, then mu minus 2. For the irreducibles, for the non-reducible, any integer can be there. Not just the natural number. See, here also we have minus, right? So integers can be there.